All right, Algebra 2, we're going to dive in pretty deep to parabolas today. The definition of a parabola. So we're going to talk about all the nuts and bolts of parabolas and how we can use them. First of all, let's do some fun little artwork. Suppose you're viewing a cross-section of a mirror. Where would the incoming light be reflected in each type of design? Sketch your ideas below. If you look, when a light hits a flat surface, it bounces back up. So each beam bounces back up. When a light hits, this looks like a 45-degree angle, it bounces straight over and then up. Okay, straight over and then up, no matter what it's doing. Okay, when it bounces here, it's going to go out. You'll see on the next slide, I drew some. Okay, so in mirror 1, the light would reflect back onto the light rays. In mirror 2, the light would reflect from one side of the mirror horizontally to the other side, and then reflect back upwards vertically. Incoming and outgoing rays would be parallel. In mirror 2, the light would reflect back at different angles because the mirror is curved. Now we have a lot to read. I hope you're okay with that. When Newton designed his reflector telescope, he understood two important ideas. Figure 1 shows a diagram of this type of telescope. The curved mirror needs to focus all the light into a single point that we call the focus. So all the light comes down, hits the curved mirror, and comes up, comes down and up. All the light comes down and hits a single point we call the focus. An angled flat mirror is placed near this point and reflects the light to the eyepiece of the telescope. The reflected light needs to arrive at the focus at the same time, otherwise the image is distorted. We talked about it. We have the focus. So it comes up to the flat plane, everything hits and comes together. This is actually the focus. I think I misspoke a second ago. So we see the light comes down, hits the curved plane, hits the 45-degree angle, flat mirror, and everything joins together at the focus. Definition: a parabola with directrix L and focus point F is the set of all points in the plane that are equidistant from the point F and the line L. So we just have a basic XY axis here. That right there is the directrix, right? And the focus point F. Oh goodness. Figure 2 to the right illustrates this definition of a parabola. In this diagram, these are all segments right here. FP1 equals P1Q1. We'll look. F to P1 equals P1 to Q1. Let's erase all of this stuff. No, I don't think I can. Okay, I assume you have this written down. If not, push pause. Because I just erased it all. F1, P1, this line segment here is equal to that line segment. These line segments are congruent. That's 3 ticks. And these are congruent. So figure 2 to the right illustrates this definition of a parabola. In this diagram, these 3 segments are equal, showing that for any point P on the parabola, so any point P on the parabola, the distance between P and F, P to F, is equal to the distance between P and the line L. So from here to the focus and here to the directrix are equal everywhere on the parabola. All parabolas have the reflective property illustrated in figure 3. Rays parallel to the axis reflect off the parabola and through the focus point F. So all the rays come down and go to the focus point F. Everything comes down to the focus, it hits the parabola and bounces in. Thus, a mirror shaped like a rotated parabola would satisfy Newton's requirements for his telescope design. Figure 4 below shows several different line segments representing the reflected light, with one endpoint on the curved mirror that is a parabola and the other endpoint at the focus. So our ray comes down, hits the point, and comes up to the focus. Okay? With our curved mirror. Anywhere the light hits this type of parabolic surface, it always reflects to the focus F at exactly the same time. Okay, figure 5 shows the same image with a directrix. Imagine for a minute that the mirror was not there. Then the light would arrive at the directrix all at the same time. Since the distance from each point on the parabolic mirror to the directrix is the same, so the distance from the parabolic mirror to the directrix, from here to there, is the same as the distance from the point on the mirror to the focus. Remember, we marked some of these. That's equal, etc. Where was I? And the speed of light is constant. It takes the light the same amount of time to travel to the focus as it would have taken to travel to the directrix. In the diagram, this means that AF equals AFA. So that's what I marked. AF equals AF sub A. BF equals BF sub B, and so on. Thus, the light rays arrive at the focus at the same time, and the image is not distorted. Let's look at our first example, finding an analytic equation for a parabola. We're going to be doing a few of these in your problem set, so let's try to learn how to do it here. Given a focus and a directrix, create an equation for a parabola. So when you see the instructions, find an analytic equation, we're trying to create an equation for a parabola. So our focus is at point 0, 2. Our directrix is the x-axis. And our parabola is going to be a set of x and y points where xy is equidistant from the focus and the x-axis. So these are going to be all of our x and y points. It's an examples here where the ordered pair is equidistant from the focus and the x-axis. Let A be any point xy on the parabola P. Let F prime be a point on the directrix with the same x-coordinates as A. So that's the same x-coordinate. What is the length of AF prime? So if we look, A is here, F prime is there. The distance here is a vertical line, which is going to be y. So no matter where this point is, even if it goes up, it's the length of y, and that would be the y coordinate of our ordered pair. So AF prime equals y. Use the distance formula to create an expression that represents the length of AF. AF is this length right here. So we have AF equals, so we're using this ordered pair and that ordered pair. We have the square root of x1 minus x2. Let's just do x minus 0, quantity squared, plus y minus 2, quantity squared. Create an equation that relates the two lengths and solve it for y. So the two lengths we had AF prime equals y, and AF equals the square root of x minus 0 squared plus y minus 2 squared. Since those segments are equal in our drawing, and we've said they're equal, then we can actually set them equal to each other. So we know that AF prime equals AF. Let's go ahead and set them equal to each other and come up with an equation. So y equals the square root of x squared plus y minus 2 squared. I can square both sides and get rid of that radical. Y squared equals x squared plus, and I'm going to go ahead and FOIL that binomial. Y squared minus 4y plus 4. Luckily, those cancel out. I'm going to move that to the other side. I have 4y equals x squared plus 4. Y equals 1/4 x squared plus 1. I have an equation that represents my parabola, which is very cool. If I graphed it, it would look just like the picture. If we can pause for a second, I just wanted to show you another drawing. We know that y is equal to square root of x squared plus quantity y minus 2 squared. Okay, the length of this line is equal to the length of this line. Okay, that's why we can set those two equal to each other. So in geometry we learned tick marks. Those two are equal, therefore we can set those quantities equal to each other and come up with an equation. So I hope that makes sense. I just liked how the drawing sort of, I don't know, pointed everything out, color coded and such. Yeah, okay. All right, verify that this equation appears to match the graphs shown. I just used Desmos, remember Desmos, and I graphed the equation we found. I graphed the focus, and I also graphed the x-axis, which is y equals 0. And we can see that, especially on points in the, that hit a grid mark, this segment is equal to that segment. It's very easy because we can count 1, 2, 1, 2. But we can do that for any point on the graph. We would just have to, I don't know, do the Pythagorean theorem or something. Okay, exercises. Demonstrate your understanding of the definition of a parabola by drawing several pairs of congruent segments. Given the parabola, its focus, and directrix, measure the segments that you drew to confirm the accuracy of your sketches in either centimeters or inches. So I took my copy of the curriculum and drew a few points on the parabola and then measured the distance to the focus and the directrix, and and then did the same thing. And I was going to not put this in there, but I figured, what the heck. This would be an example of something not quite right. And it might just be that when I printed, or when they put this picture into the teacher's edition of the curriculum, they skewed it a little bit. But yeah, it's not quite right. All right, so let's get into the meat of this. Derive an analytic equation of a parabola given the focus 0, 4 and the directrix y equals 2. Use the diagram to help you work this problem. Okay, first let's label a point xy anywhere on the parabola. I went right there, and it's xy. Then write an expression for the distance from the point to the directrix. Okay, right here. The directrix is not on the x-axis anymore, so it really is the whole length of y minus 2. Okay, that right there is 2. So the length of this segment is y minus 2. Write an expression for the distance from the point xy to the focus. Here's our distance formula. Okay, our focus is 0, 4. So we're going to do x minus 0 quantity squared plus y minus 4 quantity squared. Okay, make sure you have that written down before I turn the page. Okay, Okay, apply the definition of a parabola to create an equation in terms of x and y. So we have the vertical line, which is y minus 2, equal to the distance formula, x minus 0 squared plus y minus 4 squared. Right? Let's go ahead and square both sides. This is going to take me a second, so let's square both sides and see if we can solve it. To square the left side, I have to FOIL it. So I just want to erase that so we're not misled. I have y squared minus 4y plus 4 equals x squared plus y squared minus 8y plus 16. Luckily those y squareds cancel out. Let's keep the y's on the left side. So plus 8y gives me a 4y, and minus 4, I get x squared plus 12. Divide everything by 4. I have y equals 1/4 x squared plus 3. Not too bad, right? What is the translation that takes the graph of this parabola to the graph of the equation derived in example 1? Okay, I just brought both graphs into the slide. Okay, that's example 1, and this is our current example, right? If you remember, the directrix was a line at y equals 0. Goodness. And the directrix here is a line at y equals 2. The equation here was, let me look it up. Sorry, I want to make sure we get it right. The equation here was y equals 1/4 x squared, excuse me, plus 1. And the equation here is given. The focus is 0, 4. The focus is 0, 2. It looks like my translation is I just went up 2 units. It's the translation is a slide 2 units up. 2 units up. Let's read the problem again. I just realized I made a mistake. What is the translation that takes the graph of this parabola to the graph of the equation derived in example 1? So we don't want to go 2 units up. We want to go 2 units down. So the answer is 2 units down takes this graph to that graph. Cool. Good work. Okay, make sure you look at the lesson summary and everything we've learned, especially this point right here, even though the one that I drew and tried to measure with my own ruler didn't quite work out. But it is true, and that's really how we define parabolas.